All right, this video I'm going to talk about the first portion of the task, but in order to do that, I'm going to revisit the ready. Go back and look at the ready, and if you need to, pause it where you have the 6 different graphs of the parabolas, and you have the 6 different equations down here at the bottom. Go back and turn to that page. Again, if you need to pause it, do so, please. The point I want to make in this is if you look at that page, what is that page trying to get us to understand? Take a second, pause, and see if you can think about what is it that we discussed on that page. A lot of the discussion has been, well, the y-intercept. Okay, well, what about the y-intercept? For instance, we found -1, or this would have been 0 and -1. Let's just go with that. 0, not -0. 0 and -1. Got negative on the brain. Let's say this would have been, okay, well, what about it? Well, the connection we wanted to make was if we look at the c value, ax squared plus bx plus c, the c value tells us what the y-intercept is. So in this problem, if we have ax squared plus bx minus 1, and we look at the graph of 0 and -1, this graph goes with that equation. Right? So the c value tells us the y-intercept. The a value tells us open us up or down, stretch or shrink. That was the whole premise behind that section. And so when we look at ax minus h squared plus k, a tells us up or down, x is right or left movement, or excuse me, h is right or left movement, k is up or down movement, then what would hk be? If we can identify h and k in one word, h and k would be the vertex. That's what hk is. Now there's one other form we haven't talked about, and this other form we will get to, all right? And it's not complex, but it has an a value also. Guess what a does? G, up or down, stretch or shrink. We will talk about what these two will do later. And then when we look at vertex form, this is a perfect square. Keep that in mind. All right, now, bear with me here. I'm going to move the camera. I'm going to come back over to question number 1. And you should have these 3 done from last week, so I'm going to go through them pretty rapidly. But when we look at question number 1, if you read through the scenario, it says Grandma's going to order some stuff, and Grandma wants to order 4 perfect squares. She does nothing to them. So when we model them, this is what we have. This 4 is an a value. This a value tells me stretch or shrink, but from a model standpoint, because we kind of toggle back and forth, from a model standpoint, this tells me how many models I should have. Okay, so that helps me when we get to question number 2. Question number 2, we have 2 of the same model. Now, how did we increase each side by? Well, gee, this is x plus 3 and x plus 3. That's how I increased each side by. So if I look at one of my 2 models, how do I write a formula for the area, which again, area is equal to length times width, this being a length, this being a width, or vice versa, it doesn't matter. How do I write a formula for the area of that? That's going to be x plus 3 squared, right? So that's how I write the area for this one. But what about the model as a whole? How many models do I have? I have 2. So therefore I put a 2 out front. So this is a area model for the entire diagram. All right, well, I'm going to give you 2 other ones. Here's x squared, x, 1, 1, 1, 1, 1, 1, 1, 1, 1. Now, keep in mind I have 2 of these models. I'll show you a shortcut in a little bit. Okay, so how many x squareds do I have? I have 2 x squareds. I have 6 x's. But remember, how many do I have total? I have 12. 6 times 2 is 12, so plus 12x. And how many of these do I have? I have 9, but I have 2 of them, so 18. There is a second way of modeling it. A third way is looking at the fact that I have 2 models, and looking at each model individually. X squared plus 6x's plus 9 single units. And if I distribute, I get that second equation. Question number 3 says, hey, how many blocks do I want to focus on? I want to focus on 2 blocks all increased by 1. Okay, so if I were to underline or circle information, I would look at 2 blocks increased by 1 inch. All right, so that means I'm going to increase each side of my block by 1 inch. Remember I told you there was a shortcut from here? Watch this. Times 2. I have 2 of these. So x squared, x, and 1. Give me 3 different, well actually 2, because that's all it's asking is 2 separate ways to write this. Well, 2 times x plus 1 squared, vertex form, A stretch or shrink, tells me how much right or left movement, no up or down. Or I can say, now that I have my model done, x squared plus 2x plus 1. Or I can distribute that and I can get 2x squareds plus 4x's plus 2, not 4, 2. 2 times x squared, 2 times 2 is 4, 2 times 1 is 2. 3 different versions of the same. We have standard form, and I'll even just note that. Standard form, I have vertex form, and this is kind of partly factored form. So now, when you get to 4, look at question 4. Read through there and pause a second and see if you can underline or circle what you think is important to help you draw these models. All right? So pause it and do that. Now when you come back, it should say 3 blocks is what's important, increased by 2 inches. So again, here's a shortcut. I'm going to draw a third, essentially, of my model. Here's my original square, increased by 2 inches on each side, but this is times 3. So now when I go ahead and draw my models, hey, x plus 2 on each side. So I know that I'm going to have 3x plus 2 squared. There's one version. A second version, I can go ahead and put a 2 out front. Okay? Excuse me, I'm stuck on the previous one. A 3 out front. So a 3, and I have 1x squared. I have, count on 1, 2, 3, 4 x's, and I have 4 single unit squares. The standard form of this is going to be what? 3x squared plus 12x plus 12. That's what that's going to be. Again, x squared times 3. I have 4 x's, but this is only one model. 4 times 3 is 12. I have 4 single unit squares. 4 times 3 is 12 again. And that leads us to question 5. And this is where I'm going to stop this for today. I'm just going to make sure that the video, you can see this in the video. What would the last term be in this function right here for this to be a perfect square? In other words, what value is going to go in the square here? Well, look at this a couple of different ways. Okay, this is standard form. I'm going to kind of back it up a little bit, and when I back it up, what I'm going to do is I'm going to divide by that a value, and I'm going to take that a value out. Now when I take out that a value, I'm left with x squared plus 4x plus something. I know I have, because a tells me how many models I have, right? I have, oh that's horrible. I'd have 2 models, essentially. There's 1, there's 2. That's what a tells me, but how is each one increased by? Once I divide a out, this tells me how many models I have. This focuses on each model individually. Well, x plus 4x. Remember this 4x, I take half to one side, half to the other. So that tells me 2 on one side and 2 on the other. That's how I look at both models. But what value over here makes this one single model a perfect square? This is where a lot of you did not show your work. You take half of that middle term and square it. You didn't show your work in 2.3. So half of 4 is 2, 2 squared is equal to 4. 4 is what goes in this blank, but remember, if I have 4 for one, how many do I have for the other? I have how many total? I have 8 total. So now, take the other equation, plus 24x, and see if you can figure out what goes in this blank. And I'm going to reveal that tomorrow in the video for the next one. So think about that. Think about this process, how we did this, how I looked at each model individually by taking out the a value. So that's what you're going to want to start and do there. Ask questions, please.